Today we're going to be talking about where a function is increasing or decreasing. I have here a formal definition of increasing and decreasing, but it's exactly what you would intuitively expect. So increasing is whenever x is getting bigger, y is also getting bigger, and decreasing is whenever x is getting bigger, y is getting smaller. So if we look at this graph below, we can see we're increasing in this portion right here, we're decreasing in this portion, and then we're increasing back up again in this portion. Now, we've used the first derivative before to tell where we're increasing and decreasing, and it's exactly as you would expect, especially upon looking at the pluses and minuses that I put on this picture. So if our derivative is positive, then we're increasing. So where I see a plus, that means our derivative is positive. Our slope is increasing, and derivative is the slope. Where the derivative is negative, we're decreasing, and if the derivative is 0, then the function is constant. Now, we talk about intervals on which we're increasing and decreasing. How do we figure out what those intervals are? Well, if we're looking at this picture, we can see that where we switch from increasing to decreasing is at these points where our derivative is 0. When a derivative is 0, if you'll recall from a couple videos ago, that's going to be your critical points. So where you're 0 or undefined if we have a cusp. So if we want to find the intervals on which we're increasing and decreasing, we start by finding our critical points. So either where the derivative is 0 or undefined. And then every point in between those critical points are going to all have the same positive or negative derivative. So we just have to pick one point in there, whatever your favorite one is. So once you've picked your critical points, or found your critical points, then pick one point in between each set of critical points to tell whether you're increasing or decreasing. Just go ahead and plug it right into the derivative. Now, finally, if we want to tell where our relative minima and maxima are, this is what we were doing a couple videos ago. If your derivative is positive before and negative after your critical point, then your maximum. And again, we can see this in this picture. If we're positive to negative, that means we're rising and then falling. So we have a maximum in the middle there. If instead we're going negative to positive, then we're falling, then rising. So we have a minimum in the bottom. And if we don't switch signs before or afterwards, then we have a critical point that's not an extrema. And this is like what we saw a couple videos ago with x cubed. So this is called the first derivative test, and all we're doing here is we're saying, okay, let's find our critical points, tell whether our derivatives are positive or negative, and then that will inform whether those critical points are relative maxima or relative minima. All right, let's actually see this in an example. So here's our example. We're going to be taking a look at this fraction, and I'm going to go ahead and factor the denominator just so that we can see where our function is actually defined. So this factors to x minus 3 times x plus 1 in our denominator. And if you'll remember all the way back to unit 1, what does this tell us? Well, this tells us when we've got 0 on the bottom of our fraction, that's where our vertical asymptotes are going to be. So we know that our function is not actually defined at x equals 3 or x equals minus 1, and these are probably going to be asymptotes. Okay. So now that we've found our domain, we're going to go ahead and divide our domain up further by finding the critical points. So how do we find our critical points? Well, let's first find our derivative. So we want to find the derivative of this function using the quotient rule. Our top is low d high. The derivative of 1 is 0, so that actually doesn't even show up. Minus high d low, so this is 2x minus 2 is the derivative of the bottom, all over low squared. All right, and that's what our derivative is, and we can simplify this just a little bit more by distributing that negative 1. So we've got minus 2x plus 2 all over this big denominator. All right, so our critical points are where our derivative either equals 0 or is undefined. Now in this case, our derivative is going to be undefined at the same points that our function itself was undefined. So those won't actually be critical points, those will be asymptotes. So where is our other place to find critical points is where the derivative is 0. So let's go ahead and set the top equal to 0. Our whole derivative will be 0 when the top equals 0. So if we set minus 2x plus 2 equals 0, we'll solve for x, and that gives us x equals 1. So this is our only actual critical point. Again, even though we have places where the derivative is undefined, those aren't critical points because they're not even in the domain. That's where our asymptotes are. Okay, so we found our critical points, and they, along with the points where our function itself is undefined, are going to subdivide our real number line into subintervals. All right, so here are all of our special points. This one's our critical point, and these two are our possible asymptotes. Now what do? We want to go ahead and pick some point in each of these intervals to see what's happening in there. So let's go ahead and do that. Let's say over here, let me plug in maybe minus 2. Now you'll notice that the bottom of this, we only care about the sign, right? We care about whether derivative is positive or negative to see whether we're increasing or decreasing. And the bottom of this is always positive because it's a square. So I just need to tell whether the top is positive or negative. If I plug in minus 2 into this, I get minus 2 times minus 2 is 4 plus 2 is 6, which is not the actual derivative because we didn't plug in the bottom. But the thing that we actually care about is this is positive. So that means that this portion of our graph is increasing. All right, now let's plug in something in between minus 1 and 0. We can plug in, minus 1 and 1. Let's go ahead and plug in 0. If we plug in 0, we get positive 2 over something that's also going to end up being positive. So again, our derivative is positive, which means that our function itself is increasing. All right, now let's plug in a point in between 1 and 3, let's say 2. If we plug in 2, we've got minus 2 times 2 is minus 4, plus 2 is minus 2. Again, that's not actually the derivative, but all we care about is the sign. That's going to be negative. So that's decreasing. And we have one more interval, so let's plug in something, let's say 4. Again, this is going to be negative, and our function is decreasing. Okay, so we found our intervals on which we're increasing and decreasing. So we're increasing when we're less than minus 1 and when we're in between minus 1 and 1. We're decreasing when we're in between 1 and 3 and when we're bigger than 3. And finally, where are our relative extrema? Well, our only option for a relative extrema is right here at our critical point, x equals 1. And we're increasing before that point, and then we're decreasing, so this is going to be a maxima. So x equals 1 will be a local maxima, or rather maximum. X equals 1 itself, sorry, is not a local maximum, but f of 1 is a local maximum. So f of 1 is, let's go ahead and see what that is. If we plug it in, we get 1 over 1 minus 2 minus 3, which is going to give us negative 1/4. So negative 1/4 is our local maximum. So if we wanted to sketch out what this looked like, we actually can with the information at hand. We're going to get a little bit more specific into this in the next couple of videos, but just with what we have so far, we know that, okay, minus 1 is going to be an asymptote, and we know that 1 is going to be our maximum, and we know that 3 is going to be another asymptote. So what's going on here? Before minus 1, we're increasing, so we're going to look something like this. And then I know that I'm going to have a relative maximum here, which means that I'm increasing, but I must just be increasing up to this point, and then I'm decreasing back down again, and then I'm decreasing after 3. So we can guess that our function will look something like this. Again, we're going to get into more details about how to do this even more precisely in the next couple weeks, but this is more or less what our function is looking like, and we can tell that by knowing where we're increasing and where we're decreasing. So to recap, how do we know where our function is increasing or decreasing? We can just tell that based on the derivative. So if the derivative is positive, then we're increasing. If the derivative is negative, then we're decreasing. And we find those intervals by dividing up the number line using both where the function itself is undefined, so what's not in the domain, and the critical points. And then we can just pick a representative point in each of those intervals to tell, are we increasing there or are we decreasing?